Well, here we are with the reaction equation for hydrogen and oxygen synthesizing water. We've seen this before. And when the going gets tough, what do the tough do? Well, the tough play with Legos. So we're going to do oxidation and reduction, a basic demonstration using Legos representing the electron structure, specifically the valence electron structure of hydrogen and oxygen reacting to produce water. So let's start here. Hydrogen, or we should say a diatomic molecule of hydrogen gas. Might be a little bit easier to see if I pull these apart. So there's a hydrogen and there's another hydrogen. The red representing the nucleus, in this case it's just one proton, and the yellow representing the one valence electron of hydrogen. So yellow is going to represent, I'll write this over here, our valence electrons are going to be yellow throughout the entire demonstration. So hydrogen, we've got a pair here, proton and electron. We know that hydrogen as a diatomic under atmospheric conditions tends to form this little buddy system of an H2 molecule. But if we look, there are conditions in the electron cloud that create this attraction, but each hydrogen nucleus can still lay claim to its own electron. So we've got an electron with a nucleus, an electron with a nucleus. That's the natural kind of valence state of an independent hydrogen atom. So nothing's been shared, nothing's been exchanged, nothing's been given up. So by definition, this hydrogen has an oxidation state of 0. So every electron is directly coupled with its original nucleus. Nothing's changed from that. The 2 out front here kind of just means that we have, well, 2 of those, and we're going to need to have that there for balancing. But that's not really critical to what we're doing at here. We're really just more looking at these electrons and where they are and where they're not. If we look at oxygen, there's our O2. Well, maybe a little harder to see because of the way I had to put them together, but there's an oxygen, there's an oxygen. So oxygen has 8 total electrons, but 6 of them are valence electrons. So there on the end of the Lego piece, you can see the little bumps representing each of the 6 valence electrons of oxygen. Oxygen has the same behavior as hydrogen in that it doesn't like to exist under atmospheric conditions alone, so it forms a buddy system. So we can see there's the seam, the two oxygens put together with the blue bond. So there are our reactants, our starting point. The oxygen, same thing as the hydrogen. All of the electrons can be directly matched to their original nucleus. So I would also say that oxygen has an oxidation number of 0. So what happens in the reaction? Well, this is when things change. To set something on fire, you usually have to light it. You have to somehow heat it up to trigger the reaction. And so when you add energy to something, it tends to break bonds. So I'm doing some work here, temporarily removing these blue bonds. I'll just do one set here. And so the first thing that happens in the reaction is everything kind of comes apart. And then now it bursts into flame and it gives off light as we start to form a new bond over here to make water. Well, how does that bond happen? Well, oxygen, these 6 electrons are all tightly bound to oxygen, so none of those are going to come off. And in fact, oxygen is going to go ahead and look at hydrogen and say, hey, I'll take that. And hey, I'll take that. And it's a sharing, it's a polar covalent bond, but in principle, this is where you end up. So, I say so a lot, don't I? Hydrogen now no longer has this electron associated with it. That electron gets more closely associated with the oxygen. So if we look at this hydrogen, it's missing an electron. It's given up an electron, and the charge that would go with that is a +1. So we would say that hydrogen has an oxidation number of +1. Each hydrogen does. So this hydrogen has given up an electron, it's positive 1. This hydrogen has given up an electron, it's positive 1. So together, they've given up 2 electrons, but we would define the oxidation state of hydrogen as being positive 1. We just know that there are 2 hydrogens that have done that. So since there are 2 electrons that have been given up, electrons follow the law of conservation of mass too, they have now both gone on to the oxygen. So the oxygen, which had 6 valence electrons, has added 2, and so the kind of effective charge of what this Lego piece looks like now is a 2 minus. So we would say that oxygen's oxidation number has now become a negative 2. So notice that everything's balanced. We gave up 1, we gave up 2, and we took in 2. So the overall oxidation numbers are going to add up to the net ionic charge of the substance. So this is a neutral molecule of water. It's 0. Everything here adds up. What if we had something that wasn't neutral? Well, let's take the same thing, and what if that hydrogen wasn't here yet? And we have this little group. Well, what is this? This is oxygen. Put up a little. This is hydrogen. The oxygen would bring in 8 total electrons, 6 of them valence, 1, 2, 3, 4, 5, 6. Hydrogen would bring in 1, so that's a total of 7. But if I count everything, now I've got 1, 2, 3, 4, 5, 6, 7, 8. So I have 1 too many electrons. I have an electron that's come in from somewhere. So oxygen is still its negative 2. Hydrogen is still its positive 1, but we have this 1 extra electron that we don't know where it came from, but it's here, which means the total charge is going to be a negative 1. So here we have the hydroxide group with its negative 1 ionic charge on the polyatomic ion, and that comes from the fact that we've got 1 extra electron other than the 7 that were provided when the hydroxide group was created. So it all ties together. You just kind of have to work on visualizing the electrons and where they go. So I'm going to put this back together and try to make it look like it was back at our starting point so you can see the entire flow. Hydrogen, hydrogen, 2 oxygens in a molecule together. There's our oxygens. Water, now showing the pretty little blue bond. Another water, now showing the other blue bond. Our hydrogens are all neatly matched, so oxidation number 0. Oxygens are 0. Hydrogens given up. Oxygens taken in. And the coefficients are just saying how many of these little packages of blocks I have to build to get everything balanced. Hydrogen loses electrons. Hydrogen gives it up, and as a result, its oxidation number increases. That's the oil, an oil rig. Oxidation is losing, so hydrogen has been oxidized. Oxygen goes from a 0 to a negative 2. That's going down. It acquired these 2 electrons. An oil rig, reduction is gaining. So oxygen was reduced in the reaction. Every reduction has matching oxidation. Electrons are conserved throughout the reaction. Atoms are conserved. Everything's balanced. Everything's good. Oxidation and reduction through the reaction of hydrogen, oxygen to produce water. Awesome.